All right, everybody. So in this video now, I want to shift our attention to partial isometries and positive semidefinite operators. So in our prerequisite notes, let me give the definition that is there of a partial isometry. And these are going to be very much related to projections, and they play very nicely, in fact, with projections. Um, so definition, we say that V is a partial isometry whenever V is equal to V star V. Um, so this is a very algebraic looking characterization. And admittedly, this is the easiest definition to give algebraically, but it does seem a little bit funky and kind of, at least for me, when I'm looking at this, I don't see a ton of intuition just from this formula. So we're gonna take a look at this formula and actually see some nicer ways to spatially think about what these things are. So let's make some observations first from this. So observations. Well, let's note that if V is a partial isometry, okay, if V is a partial isometry, well then I claim V star is as well, and let's see why. Well, V star is going to be the adjoint of V star V. And if I follow my adjoint rules carefully enough, this will be V star V star. So this instantly implies that V star is also a partial isometry. Okay, so that's the first thing to note is that if I have a partial isometry, so is the adjoint. Um, two, um, um, if V is a partial isometry, implies V star V is a projection. Now, the nice thing is that we already have a very algebraic characterization of projections, and this is an algebraic formula, so we probably want to go ahead and use our algebraic characterization of projections. So why is this going to be true? So why? Well, we first note that V star V is self-adjoint. V star V is self-adjoint. And if I do V star V squared, that's going to be the same as V times V star V star. Sorry, let me copy it better. Sorry about that, everybody. Let me do better about my copying. Sorry. This is V star V star V, but now by definition of partial isometry, this is just V. So I get V star V. Cool. So V star V is a projection, and then this also means that because V star is a partial isometry, so similarly, since V star is a partial isometry, we also get that V star is a projection. Okay, so as to our projections. And in fact, um, you want to this characterization, you can in fact define a partial isometry as something where V star is a projection. And so for further discussion, see exercise 1.48 in the prerequisite notes. Okay. All right. One other observation to make before we go on. Note that any projection P is in fact a partial isometry. Um, it isn't as useful to think of it as one, but it's nice that it is there. We kind of view projections as sort of very static partial isometries, as we'll talk about soon. And partial isometries in general, we kind of view them as being more dynamic in that they kind of move a piece of my space isomorphically onto another piece of my space, or isometrically rather. And in fact, that is the next thing we're about to show after a key definition. So given a partial isometry, given a partial isometry V, sorry, maybe given a partial, sorry, too many thoughts in my head at once. Let me move this down. I think I would be remiss at this point. Any projections of partial isometry, also any unitary is a partial isometry. So remember, unitaries are ones where you start a U as the identity, which is going to be U used. And in fact, I'll say a bit more about this in a bit, about why I included that example. So given a partial isometry V, we let its source projection be V star V, and its range projection be V star. And maybe I'll just kind of draw why we give them these names. Why do we call them that? Well, if I take a V, you want to think of it as going from the source to the range, source to range. And so the idea is that, well, if I put what should be my source here, that's V star V, and we saw that that was just V. So i.e., multiplying by the source projection does nothing. I.e., it should sort of this should stabilize what V does. And similarly, if I go the other way, then I do V star times V. So if I can act on the range side, well, that's again V star V, which gets us back to V. So just kind of where you put these projections kind of tells you why they should be called source and range. These kind of stabilize V on either side. But there's now a very spatial way to think about this. So before I write anything down, I'll just say this in words. Unitaries are things that you have learned preserve, or isometries more generally, but I'll say unitary specifically. Unitaries preserve lengths there. And so the thing about a partial isometry is they're going to do that as well. However, to be precise, we're going to have to restrict to the subspace determined by the source projection. All right, so we're going to set to this, we're going to set S to be V star VH. So it's the, all right, so because now we know that this is a projection. So it's going to be this subspace of H, projection acting on H, and R is going to be the image of the range projection. So V star H. So the theorem, and this is theorem 8.4, Um, um, V restricted, so V restricted to the source and V star restricted to the range are isometries. Moreover, V will map the source to the range. V maps the source to the range, and this is an isometric isomorphism with inverse V star restricted to the range. Okay, so this is V kind of restricted to the source. So V restricted to the source is an isometric isomorphism with inverse V star restricted to the range. Okay, let's prove this. All right, so, well, if C is in V star VH, well, then since V star V is a projection, because C, this in fact will imply that C is going to be equals V star V C. All right, well, what is that going to tell us? This tells us that VC against VC is going to be V against V, sorry, C rather, against V star V C. But then in turn, this is just C against C. So, i.e., this preserves the magnitude squared of C. So we instantly see here that V restricted to S is an isometry. And we'll say by a similar argument, V star restricted to the range is an isometry. Okay. Now we just need to show that V is going to be an isometric isomorphism mapping S into R. Okay. Well, let's note that given C and S, C has to be equal to V star V of C, which implies that VC is going to be V of V star V C. And we're going to rewrite that as V. I'm going to rewrite that as VV star of V of C. So this is VV star of something. So this is certainly going to be in VV star of H, i.e., this is going to be inside the range. So at least we're mapping from the source into the range. And then to show it's an isometric isomorphism, well, I have a ready-made formula for the inverse. And so we see that that V star V acting on C is inherently going to be C. So that shows you that V star is a left inverse of V, right? Because of how this works. So for C in S and for eta in the range projection, well, V star eta is eta. All right. So this shows that I have a two-sided inverse between S and R. So this tells me that V going from S into R is an isometric isomorphism. Okay. So so this is going to nicely map S to R. So let me kind of draw a little picture here so far of what we have here. So one way I can break up my space here is I'm going to have an S, and here maybe I have my space R is here. And the idea is that V maps S to R isometrically. But we should also note that, or what I claim is that V restricted to the orthogonal complement of S, like V restricted to the orthogonal complement of S, is going to be 0. That's what I claim. And so why is this going to be true? Well, the projection onto S is given by V star V. So it's enough to show, well, so we're going to take V and we're going to act it on 1 minus V star V for C. Notice that this here is the projection. This is the projection onto S perp. Well, what is that going to be? Let's drag this down here. This guy is going to be V minus V star V acting on C, which will just be V minus V acting on C, which will be 0. So on these complements, this thing kind of does nothing. So that's why the word partial isometry is really used here. It's the visual interpretation is that on a part of a space, it is an isometry. It's just that on the orthogonal complement, it is not. And a comment, this is exercise 1.50 in the prerequisite notes. This spatial realization is actually equivalent to seeing that you're a partial isometry. Namely, if, say, W is in B of H, K is a subspace of H, closed subspace, and if W restricted to K is an isometry, and W restricted to K perp is 0, then W is a partial isometry. Under the algebraic definition, i.e., it must be the case that W will be equal to W star W. Okay, so that's about partial isometries. Hopefully this picture gives you some idea of what's going on here. They are very prevalent, especially in the area of von Neumann algebras, and to some extent as well, C-star algebras. They play a huge role in talking about equivalence of projections, which is something that you will see later. Okay. Finally, just one final class of operators, talk about positive semidefinite. we say that, let me scroll this down. We say that some operator x in B of H is positive semidefinite if xc against c is bigger than or equal to 0. So this is real and bigger than or equal to 0 for all c in H. So a fact. So let's note if x is say y star y for some y in B of H, well then xc against c is going to be y star y c against c, which will be y c against itself. Sorry, let me write this both down a line. Whatever this thing is always bigger than or equal to 0. So this tells you that x is positive semidefinite. And there is some, intuition here if you just think about complex numbers, because this is sort of the analog of taking a complex conjugate times the number itself. And hopefully we know from our complex variables classes that that is just the absolute value squared. Complex numbers is something positive. So this notion does carry over to operators. And in fact, you will see, so later, you're going to see that x is going to be positive semidefinite. If and only if x is going to be y star y for some y in B of H. Okay, x is positive semidefinite if and only if x is y star y for some y in B of H. You will develop the tools to prove that later, but perhaps I will end with an example. So let's suppose A is an n by n matrix. This will be positive semidefinite. So first note that AC against C is at least has to always be real. And so by exercise 1.5, let me double check the exercise number. Exercise 1.5, sorry. 1.53, sorry, exercise 1.53 in the notes, A is going to be self-adjoint. But also, let's note that A is self-adjoint, and so since it is self-adjoint, we know that A is diagonalizable since it's a matrix, so it has eigenvalues. So and it's orthogonally diagonalizable. So if lambda is an eigenvalue, with eigenvector C, well, 0 is certainly less than or equal to A C against C. Which by rule is lambda C against C, which would be lambda times the norm C squared, which instantly tells us that the eigenvalue has to be bigger than or equal to 0. Consequently, this implies A is equal to some unitary U n times this diagonal matrix D with entries lambda 1 through lambda n on the diagonal. And then U star. And so if we set D to the 1/2, this will be later be what we will call the square root of D. And then we're just going to square root each of the diagonal entries. Then A is certainly going to be U D U star D to the 1/2 U times itself. And sorry, or of course, I should have stated here that U is a unitary. And so you get something star times itself. And so this shows that this claim that I have here is at least true for positive matrices or non-negative matrices. So it's true in the n by n matrices. And part of the goals, the part of what you're going to learn here at goals is that this is going to be true in a general C star of von Neumann algebra. All right, so this is it for the prerequisite notes on projections, partial isometries, and positive semi-definite operators. I hope these will be useful.